we were working on our first numerical example on designing a beam. And, also what we did is we did the quick derivation of the equation over there. So this is, we derived this equation, and this equation is going to find for us the minimum area of steel to resist this amount of moment based on concrete strength and also concrete dimensions like B and D as well. Okay. So very simple, straightforward. We found out that the minimum area of steel to resist such moment is 3,134 square millimeter. Guys, the thing is we cannot place exactly this number in our beam. The reason is we simply have to pick some bars from standard available bars. You guys know the bars are 10, 15, 20, 25 m, all the way to 55 m. So we cannot tailor our rebar to give exactly 3,134. We choose among existing bar designation. So when we choose, for sure we cannot get exactly this number, and we have to place more than this number. Because as soon as we place less than this number, then our beam is called under design, which means my beam is going to fail if it's exposed to those slot loads. And that's where I said before that along the way, we start from MR equal to MF. And then along the way, we will make sure that always MR will be more than MF. And this one thing we do, if we place area of steel more than the minimum required by the equation, then for sure our moment of resistance or the beam capacity will exceed the MF. Now, I think Gord, I like it so much. Like if things start to get sense, like make sense for you, and Gord, I think at the very last of at very end of the class, he said we have so many options, not only one option. If we're trying to place this much, we can use 20, we can use 25 m or 30 m, and you can see here I kind of compiled this table for you. So if we chose to use 20 m, then we know that every 20 m has a cross-section area of a 300 mil square, and we need 11. Okay, so it's not very like high math. Just you divide the 3134 divided by 300, you will get like a number, not integer. But what you have to do, you have to get the next integers. For example, you will get 10 point something, and then obviously we cannot add 10.5 bars. We have to use 11 bars. Okay, so 11 bars, you go back, multiply 11 times 300. This will give you 3,300. We can also choose a different bar diameter. Let's say I'm going to choose 25. So 25 each is 500 square mil. And then if I multiply 500 times 7, so that's 3,500. I can also go with a 30 m. If I go with 30 m, every 30 m, the area is 700 millimeters square. You multiply 700 by 5 bars, then you end up with 3,500. One more time, all these numbers, it has to be above the minimum given by the equation. Now, this is a broad discussion, and you can see we have many options. And to be honest, there is not as like a single answer for this problem. Should I use 1120 m, or should I use 725 m, or should I use a 530 m? So here I try to make some comments, and hopefully this will lead us to the choice. So I said here, if we use 1120 m, our area is 3,300, which you can see among those three options is very close, or the closest to the required, which means if I use this one, it means I'm saving more material because it's very close to whatever required by the equation. However, the problem with this one is it is too much work. If you work in in rebar, you will see every single bar we have to tie it into the stirrup to make a cage, and tying rebar is time consuming and it requires more work. So that's, I said here, too much work to tie it to rebar. Okay, now On the other hand, if you look at option number 2, number 3, yes, we're getting a little bit extra waste of material, like because we're simply adding 3,500 while we need only 3,134, then we're wasting a bit of material. How about the labor? We only have to tie 5 bars, then we get less labor. Now, which one should you go with? It depends on where you build this beam. If you guys build this beam somewhere on the earth where the labor is so cheap, then for sure, if the labor is so cheap, so you don't care much about tying rebar and you go with 1120M. If you go somewhere on the earth where the rebar is so cheap compared to the material, then here we go. Like in Canada here, which one is more expensive, labor or material? Do you have a car? Anything in Canada here is kind of fixed rule. Anytime you do something, you will see the labor is more expensive than the material. Would you agree, guys? Needs to hear some noise. Anybody has a car, try to fix the car and see how much is the part and how much is the labor.
Yes, I agree with you because even in the Philippines, it's the same thing. The labor, when you build a house there, the labor is more expensive than the materials. However, my idea is when choosing the sizes of the rebars, I think first of all it depends on which um uh building components are you going to use it. If it's in column, so depending also on what is the characteristic of the soil in that area. So then you can be able to choose which rebars are you going to use, and also in the column mostly a little a little bigger sizes compared to when you use it in the beams.
Okay, thank you so much for this input. I disagree. Like, yes, of course, the bar size, it is function of the thickness of your member or the minimum dimension. If we are reinforcing slabs and slabs in general, I'm not talking about raft slab. I'm talking about just slab, like one of the floor slab. So the slab is typically 6 inches or 8 inches or maybe maximum 10 inches. We don't place like 25 or 30 m in this slab. Probably we place 10 m or 15 m. If you're trying to make a raft slab, and the raft slab is sometimes it's 1.5 meter, 5 feet deep. In this case, you will see 25 and 20 m and probably 30 m. So for sure, the bar diameter is function of the thickness of your element, for sure, 100% correct. So that's one thing. The other thing also, when you place more rebar, it looks like we're getting more resistance. And so more resistance typically for more important item in your building, we typically kind of become more conservative and we add more resistance. Because simply look at the column and the beam. What happens if the slab, like the beam fails? If the beam fails, then your building is not going to fail. Still the beam and what is supported on the beam, which is a single floor. How about if you have a column failure, then this is a big deal. And that's why I'm going to go into this discussion, but not now. When I design my column, I will always have a more margin or more reserved capacity in my column. But thank you for this input, okay? So guys, I'm gonna make it easy for you. Here we go. I said here, let's use 530M because let's say we're doing this in Canada. I'm going to consider the price of the labor, and it's okay to waste some material. That's fine. So I'm gonna use here 530M. And I know some of you will ask, so what happens in, guys, do you hear me?
Yes, I
Yeah.
can.
Okay.
Because I get here a message that my audio is not shared. But anyway, so what happens here is in the assignment or in that midterm exam, final exam, any exam, I'm not gonna let you like loose. Huh? I'm going to fix it for you. I will give you the bar diameter, and all what you have to do is just choose the number. So the bar diameter will be always given to you. If you're designing a beam, I will say use 20 m. But I wanted to run this discussion so you understand in real life you have many options and it depends on so many other factors. Okay, now once we say that I'm trying to place in my beam a 30 m, what happened is you need to make sure that those 530 m are going to fit into one layer or two layers. The thing, guys, here that we have made one assumption. You can see if I go back in the slide, to this slide here, when we started, we said, okay, you know what? Yes, H, which is the depth of the beam is known. However, since when we start the design, the layout of my rebar is unknown, and that's why D prime is unknown, and D is kind of combination between known and unknown. And we made the assumption that the D prime is a 70 millimeter to compensate for, for cover and stuff like that, and cover stirrup and half bar. So, however, as I said, assumptions are great. They make our life easy, in terms of mathematics. However, don't ever say that I finished my design without verifying the assumption. So it is time to verify the assumption right now, since we're very close to finish our design, because we have a 5 bars. In order for us to like check the depth or the D prime, we need to answer this question. So my rebar, is it going to be one layer or two layers? Because think about it. You cannot find the D prime, which is here on this picture here. D prime is simply function of how many, like the bar diameter, and do we have one layer or two layers? So probably it's time now to do that. So it's very simple. You guys know that our best bet is to put all the rebars in one layer. Does anyone in this class know why? Show your hands, please, if you know the answer. I'm going to say it one more time. We said we're trying to figure out if my rebar can fit in one layer or in two layers. And I said our best option, our best bet is my rebar to fit in one layer. One layer. Gold.
It's less material, less time, and less labor.
Can you tell me why less material? Because I already said I need 530 m. Why do you think it's less material?
Well, for that case, maybe a little different. But if you can get it in one layer, then you use a bigger bar.
Okay, thank you.
But for 5, I guess for 5, you can't do it in one layer unless you increase the width of the beam.
Okay, thank you. So let's go with Diego. Diego, what do you think?
I think that if you place it in just one layer, you can lay it out before putting the concrete. If it's in two layers, you will need to pour the concrete and then put the other layer, or put some support to create that elevation difference between the layers.
Okay, I need to answer you because what you said is not right. Like, and I need some support from whoever had some experience on site. Anybody? So please put your hands down, and I'll go back to this question shortly. But let me ask you: anybody like who attended putting concrete in beams, wherever, two layers or three layers, or even doesn't have to be a beam, even for some like walls, like do we need, if I have more than one layer, do I place some rebar and then add some concrete and then add the rest, like the rest of the rebar? Okay, please go ahead. I would say, let's say I'm gonna go for both of you. I will talk to Mahdi first.
The rebar is placed before we pour the concrete. We don't have to keep going layer by layer, adding more steel and then pouring concrete again.
Okay, so what holds the rebar in place, sir?
The ties.
Ties. How about you, Gord? What do you think?
I've poured lots of concrete. I just maybe misunderstood the question. Typically, you have stirrups that hold up your rebar when there's multiple layers.
So you tie the rebar to the stirrup. Even second or third layer, you tie the rebar to the stirrup. And I know some of you will say, what if I have a rebar that not close to the stirrup? I mean, if you don't follow the discussion, give me some time, I'll show you. So if you go back to this section here, and let's say I'm gonna put here one more layer of rebar. Here, one there, another one over there. Diego, I want you to listen to me, please, huh? So if you have those like those two bars, and you can see those two bars, they are very close to the stirrup. So we tie them. We tie this guy to the stirrup, and we tie this guy to the stirrup. And so we tie this to the stirrup. How about if I have another bar here on another layer? You can see it's in the air. How do we hold this bar in place? Anybody knows?
Is it a dowel?
Put another horizontal stirrups.
Gord, what do you think?
For those bars, what we've done is we've used booster chairs to get your coverage.
You know what, like chairs is one option. You put some little bit of piece of rebar that holds this in place. But I would say sometimes what we do is we place, something called like a tie. I know that that's the name, but probably you guys know different name. So we simply have a tie. I'm sorry, like a tie, and this tie, it goes through the forms, and simply you simply, so this tie here will support those bars. This is very typical in walls, because in walls there is no, like I'm talking about frost wall, in walls there is no stirrup at all. And how do we hold rebar in place? Sometimes there are so many ways, to be honest. Like I've seen so many ways on site. Some people, they use like those wires, and they have like some sort of a cross member like wood, and then they tie the top bars to the wood. And some they put those, because this one also, it keeps the width of your beam constant, because you're pouring a lot of concrete, and if especially you have a very deep beam, you have a very lots of pressure at the very bottom. So this tie here will keep the width of your beam. Are you guys following? Are you following?
Yes.
Okay, so again, Diego, it's not we bought it. Okay, guys, looks like you're not really focusing so
Yeah,
much
but
with me.
that's what I mean. Like when you have to put a second layer, you need to do some extra work to hold it in place.
So I misunderstood you. I thought that you meant that you place concrete first, and then after you
Yeah,
poured some
I
concrete.
said that, but I didn't thought about that really well.
Okay, no problem, no problem, guys. To be honest, I don't want to. I know some of you already have been to sites, and everything I say now, we combine theory with some of your experience. And trust me, if you have some experience before, this course will make a lot of sense for you, because you've seen some stuff, but you never knew why. Now it's time to know why. So, but even if you have zero experience, you will survive my course, and I'm hoping that you will love my course. Now, again, I'm gonna, since nobody answered really my question, I said why our best bet and our best option is to place one layer of rebar. It's simply because when we place our rebar on one layer, so all the area of steel is at the very bottom of our beam. So the lever arm will be a large lever arm. Once we place our rebar on more than one layer, what happened to the centroid? Centroid goes up. And if centroid goes up, then I lose lever arm. And if I lose lever arm, it means I'm kind of losing beam capacity. Okay, so our best bet, if we can, we want to place our rebar on one layer at the very bottom of our beam to get the longest lever arm. Okay, now, so I'm trying here to make sure, or to check, not make sure, to check if my rebar will fit into one layer. And probably that's the first exercise to do that. So you can see here, by the way, there is no sine, there is no cosine. I'm trying here to check whether my beam with the given width can accommodate my rebar. Now, very simple, watch me please. So I'm saying here B minimum. B minimum is the minimum beam width that can accommodate the 530M with 10M stirrup in one layer with a proper cover and proper spacing. How do we do that? look at this equation, please, which is not super science. This width that can accommodate all this condition here, is very simple. You say, okay, you know what? I have cover from each side. So 2 multiplied by the cover, whatever the cover is, plus 2 multiplied by the stirrup, and then plus n, and n is the number of the rebar, multiplied by the bar diameter, and then finally plus n minus 1 multiplied by the spacing. Now, please look at this picture. You'll get this. So I need cover from every side. So here is my cover. Here is my cover. So I multiply by 2, and then 2 multiplied by 10, which is my stirrup. And then I have 5 bars. So 5 multiplied by the 25 millimeter bar diameter. And then count the spacing. So here is 1 spacing, 2 spacing, and then 3, and then finally 4, which is n minus 1. If you have 3 trees, so you have 2 spacing. So it's always n minus 1 multiplied by the spacing. Now, what happened is, if you put all those together, you will get 398. Can we read this in plain English? In plain English, it means if I make my beam 390 millimeter wide, it can accommodate my 5 bars with a 10 stirrup with the proper cover and the spacing according to the code. Now, there is one thing I didn't give you more details about it because we've done it in the past. This number here. What is this number? The 42. The 42 is the spacing between the rebar. If you don't know how to find this number, please study, review the material. Somewhere I gave you how to find the spacing. It is 1.4 bar diameter, or 1.4 maximum aggregate size, or minimum of 30 millimeters. So I'm telling you here that the minimum width that can take all those items is 398. Are we okay or not okay? Here is the answer. If my beam is 450, 450 is more than 398, it means the answer is yes. I can place my 530M in 1 layer of rebar. Okay, now once we know that, now we can go and verify our bending assumption. Need to remind you, where is my bending assumption, which made my life easy and enabled me to proceed and find some area of steel? It is this assumption here. So what we do is very simple, not very difficult. Now I know that I'm going to place my rebar in 1 layer, and let's see. So what we have to do is we need to find our actual effective depth. So what was this number? Like the 530, you can see here in my solution, sorry, I had 830. So where did I get 830? 830 is 900 minus 70. And 70 is just a reasonable assumption for the cover and a stirrup and half bar. Okay, now time to verify. So what we do here, we do a D actual, not D assumed. So the D actual, because I know how many bars, I know how many layers, I can say, okay, so D prime, which is from the bottom, equal to the cover, plus the stirrup, plus 1 bar diameter over 2. So we get 55 millimeters. So now if you want to find the D actual, you're going to say 900 minus 55, that's 845. And this happens to be more than what I originally assumed. Remember, I assumed 70 for D prime, and I got D equal to 830. However, now I'm almost finishing my design, figure out that my D is equal to 845. Remember, this is called the D actual, and this is called the D assumed, because it's based on assumption. Now, I'm asking you guys, okay, and we need to run this discussion, are we okay or not okay? Like, like I started my design and my D assumed with 830, and then once I found my area of steel, turned into rebar and bar diameter, figure out that my actual D is 845. Okay, what do you think? Is that good or bad? Is it good news or bad news?
Bad news.
Good news.
Okay, let's start with Mahdi. Mahdi, why you think it's bad news?
Gordon said bad news, but yeah, it's bad news because we kind of I'm assuming we underestimated what the actual depth would be.
So you think if I go back to the equation and I replace my 830 by 845, I will get area of steel more than I got before, like 3134, or I will get less? That's the same question, by the way, in different language.
Yes, you will get more.
Okay, so since you do that, now you do it right now, please. Everyone in class, please. Just go to the same equation one more time. Let me show you. So everyone, I want everyone to convince, and there's no way to convince you except is, please, you can look up my screen, repeat the calculation based on 845. So cross this one, do it one more time, and tell me what is the new area of steel. And let's see, are we gonna get more area of steel than this number or less?
Wouldn't you get
Everyone.
less?
Excuse me?
Wouldn't you get less?
Please, I mean, don't say just do it. Please do it. Follow what I said and do it. Fine for me. Area of steel based on your actual D, which is 845. It's gonna take a couple of minutes, but will save us a lot of headache. Okay, because you've done it, you feel it. Do it, please. Please, I want everyone, even if you feel that it's the opposite, please do it. As I said, when you do with your hand, there is no way for you to doubt what I'm gonna say.
Can you go back to the formula?
Sure, I will. But you guys, I want you, all of you guys, by the way, please, whenever I teach, have the PDF open as well. Maybe yes, you look at, but make it minimize. So just in case I ask you to do something, you just look at your PDF, not my screen. Okay. One more thing I want to say, which is related to the material. So guys, I'm keep working on the material. Try to become ahead of you because this material is very, very warm. Just prepare like, like this morning. Okay, so you will see on the D2L, you will see a kind of a newer version of the Beam design. So all I'm asking you is please, probably every class you need to download and then don't print because I'm changing my stuff. Not really much. I'm adding maybe, but I don't really change the previous slides unless there is an error. But as soon as we finish all the material, then please go ahead and download the final version. And if you want to print it, that's up to you. Okay. Do we have any comments? Like somebody commented?
It is less, sir. The area of steel is less than
Yeah,
the.
3,062.
Yeah, I got the same
So
one.
guys, I mean, thank you so much, Gord. You texted, you said that, and I like what you said. And we just said it, guys. The area of steel is connected to the lever arm. Whenever I increase my lever arm, I need less area of steel. Because I said, do you remember the example when I said, where do you open your door? Do you open your door, you push at the hinge or you push at the handle? For sure, when you push at the handle, it takes you less force to open your door. If you push close to the hinge, it's very difficult because your lever arm is so small, okay? Anyway, so what happens here? Yes, if you increase if you get a D actual more than D assumed, which is our case here, it means that's really good news because we're getting a lever arm larger than what originally anticipated, and for sure, I can go back and change my equation and to use the 845, and maybe this is going to save me some area of steel. Let's see what I. So the beam, so what exactly what I said here. The beam will have a larger lever arm than what we originally assumed. Refining the AS is not mandatory. So you can see here, when I got 845, then it is up to me. I may or may not, it depends on if I have time or no. If you are a designer and you're designing 10, 20 beams per day, so you're so busy, you say, okay, you know what, here we go. I'm very safe. I'm going to, keep going. However, if you have time and you want to go and refine your results, as we did a minute ago, when we used 845, then we got how much? Anybody help me out? How much?
3062.
62. Okay, so I'm gonna write it here, guys, because that's really a good example. 3062. Now, if I still use a 30M, what do you think?
If you use 30M rebar,
Yes, nothing is gonna change because there is not. If I use 700, so 700 4 bars is 2800. So I cannot use 430M. You can't, because you will be below the 3062. How about if I decided to change my decision and I go for 25M? Even with 25M, each one is 500. So I'm going to get 6, correct? But 6 is 3000 only. So I'm short of 62 millimeter. And that's why I will use 7. So you can see so it's up to you. Please read my statement very carefully. So I said here, refining the area of steel is not mandatory. It may, and you can see I wrote it in red, it may yield to some saving in your rebar, or it may not, just like this case. Because when I refine my results and I used 3062, okay, looks like I cannot do it with 30M. No, sorry, I'm gonna get the same number of 30M. And I know some of you, if you're really awake and you're following exactly, say, Tahir, no, 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 wait. If we use 25M, this D prime here will have to change as well. For example, let's do that. So if I say here, if I use 25M, then D prime doesn't stay the same. So D prime will be 30 plus 10 plus 25 divided by 2. And this will give you how much? Will give you 52.5. Yes or no?
yeah.
And then how about the D? So the D will be how much? Will be your 900 minus 52.5. Any help? Any help?
847.5.
47.5. So which means, hey, Tahir, listen, don't deceive me. If you want to get the area of steel based on that you're going to use at 25M, this is the D. It's supposed to go to your equation. Is anybody has like a Excel open or something can do that very quick for me? Like go back to the equation here and use the D, not 830, not 845. However, please use 847.5 because this little amount of 2.5 millimeter maybe is going to offset your 62 millimeter, and maybe we can live with 625M. Okay, I'll leave the guys for you if you wish. Take a note and do it when you have time.
3051.
So still, those 2.5 millimeter never helped me. So my statement is still true. I said here may yield. So it may or may not. May yield to some saving. Sometimes the number, because my numbers here was a little bit off, but sometimes you are on the edge. So maybe a couple of millimeter in your lever arm will simply put you in a one less rebar. One less rebar. However, look at this. Please read the next one. And the next one I cannot, so it's not may. However, if the actual lever arm is less, so let's say you're assuming the actual, and this is not what happens. You assume the actual, and it happens to be less than the assumed. What happens? What do you think? If your actual D is less than the assumed based on the 70 millimeter,
Then you got to change. Then you got to change it because
the
less is
area of steel you need is going to be more for sure. If we use this equation here and we use 820, what do you think? Without any calculation, if I use this 820 here, what happens to the 3,134?
becomes bigger.
Exactly, it's going to increase. It's going to increase because we're losing lever arm. And we have no guarantee that what we chose before is going to cover this extra. Okay, so I said here, whenever or however, if the actual lever arm is less than what was originally assumed, repeating the calculus of area of steel is mandatory in uppercase letter, underline, bold, red. So I don't know what else I can do to tell you it's mandatory. There is no other choice. That's unlike if your D actual is more than the assumed. Okay? Hopefully this makes for you.
Then,
But
Tahir, why do we why do we assume then? Because in most cases, wouldn't the D actual always be usually be less than what we assume?
Dominic, because we
okay,
don't have the
no, I'm here. I'm
identification.
here. I'm here. Okay. I'm here. I'm here. I'm the boss. I'm the boss. Sorry, but I'm the boss. If you want to teach him, you can teach him, and you can even get coffee in return. But I'm the boss here, please. If you want to teach him, just raise your hands and respond to him, please, because I'm just facilitating this. Huh? You want to take over, Jelly? You want to take over?
You're the boss.
Oh, you're mad. Guys, okay. Anyway, uh, I didn't mean anything to you guys. Just, it's a class and I want to control the discussion. And especially, I don't see you. So please, if you want to say something, please just ask me before. Thank you. Uh, so the answer to this, you see, you started an and you said in most cases this is what's going to happen. Your G actual will be more than the assumed. Is that what you said, Domenico?
Yeah.
You know what? Can you please wait until next week and I will show you that this is not true. I have here, and you can enjoy if you wish. You can enjoy. I prepare a class this morning, and if you go to the last part of my slide, and here we go. So this example here, if you want to entertain, go to this one. You will see what you said is not a true statement. It means not all the time your D actual will be more than the assumed. Okay? So it's just at the end of the day, we have to check. We have to check. Okay? Now, guys, so what happens here? We're good because simply our D actual is more than the assumed, and we're okay, and we don't have to repeat. But I also mentioned something which may look weird for you. Please read this statement. I want everyone to read this statement. And I said, although it is mandatory, it's mandatory. If you lose some lever arm than what you originally assumed, so not your choice. You have to repeat the calcs for area of steel. Okay? However, you may end up with the same result. Does it make sense for you? Is that statement contradictory to what I said? Hello?
No, it's all good.
Okay, can I hear somebody else? Hello? It's only Domenico?
I'm trying to make notes here while you're yelling hello. You got to give a guy a minute before he can speak up.
See, if you turn on your cam, I will do that.
Tahir, so you could say that the rebar to concrete beam ratio is kind of like toilet paper. Less is more.
What does that mean?
You never watched the Charmin commercial? 10-ply toilet paper, less is more. That's what you're trying to say here.
That's exactly what he's trying to say.
Did you finish your notes, Gord? Guys,
Yeah,
the thing
I
is,
finished my notes. I got it highlighted and everything now.
perfect. So, I mean, I'm gonna ask you to turn on your camera as long as you can, because at least gives me some kind of feeling of what's going on. I'm here. I'm just ended here. I don't see you guys, so I don't know what's happening. Are you mad? Are you? I know somebody is mad right now.
Oh, I am not mad. I just wanted to explain Dominic that
I have
when
no problem with that, but the
when he
thing
asked
is,
when he asked like what to assume, because in the beginning we don't have any data yet, so we need to assume something.
Yeah, of course, yeah, and that made our life super easy mathematically. I don't know, like I don't know what can you do if there is this assumption doesn't exist. Okay, but anyway, I'm again all my trying to say here is that please read this statement, and I know sometimes this looks confusing. Like how come you say it's mandatory and but may not change your results? I mean, that I'm not saying your results. Your area of steel, the new one, for sure will be different and will be more than what you get initially. But remember, we're not really picking exactly this number. We have to choose among existing rebar. Rebar that does exist. We don't have a 24 mil. We don't have 23 mil. We have to use 25 or 30 m. So maybe your 530 m is still covering you up. Okay. Now, guys, once I mean, in our case here, we're okay because our D actual is more than what we originally assumed, which is fantastic. So I don't have to go back. If you have time, yes, do. And it doesn't have to, maybe it may not change. And we already figured out it will not change my finding. Remember, what is my finding? I'm going to use 530 m. That's my final finding. This doesn't change. Now, are you guys typing anything in? Okay, thank you, Michael. Now, guys, when we are done with this part, it doesn't mean, and you will see how long is my design process. It doesn't mean that we are done yet, because simply we have to ensure or check our failure mode, or the beam failure mode, not our failure. I always say I and we, but it's the beam, it's not us. It's we need to check the failure mode to make sure that the failure mode is ductile, which is very simple. By now, after we went through all the pain of whether the strain diagrams or maybe the C over D, that will be our standard method in our design. We simply have to find row balanced, and the row balance is as simple as your F prime C divided by 1100. So for a 25 MBA, your row balance is 2.2%. Any beam that has 2.2%, it's a balanced failure. Any beam that has less than 2.2%, it's tension failure. Any beam that has more than 2.2% will be a compression failure, given the F prime C is 25 MBA. And what happens here is we need to find what is my reinforcement ratio. So this number here is balanced reinforcement ratio. It what turns your beam into balanced failure. How about this one? This one is the actual reinforcement ratio in your beam. Rho. How do we do that? Very simple. We say we've ended up placing 5 bars of 30 m. So 5 times 700. So that will give you the total area of steel, AS, and you divide by the width of your beam, which is this number here, 450, and then divide by the depth of your beam. Now, something that I always see over the years, students, what they write here 830. 830. Is that correct or wrong? 830 is correct or wrong? Obviously, it's wrong, because I used 845. I make it red to just bring your attention to we use the actual beam depth, not what we originally assumed. If you do so, you will get a 0.92%, which is way less than 2.2%. This means tension failure, ductile failure, probably reinforced, whatever you want to say it is okay. Now, any questions so far, guys? Any questions so far? Somebody's typing some.
I kind of got a question about that. If you could go back to, yeah, right there, it says 0.92, and then you keep saying it has to be greater than 2.2.
Did I say it has to be greater? We said, Domenico, we said what drives the beam to fail in compression is we have so much rebar. So which means the area of steel is so much, so it forces concrete to fail first, which is bad. Which means it's opposite to what you said. It means it has to be less.
Sorry, less than. So then, no, I just answered my own question then. Never mind, sorry.
Okay, no problem. Okay, guys, next is the code asks for a minimum reinforcement. So you can see here we're trying to be away from maximum reinforcement, because if my beam is overly reinforced, it means it's going to be compression failure. On the same time, the code has a minimum reinforcement in the beam. And you know what? I'm going to delay this line for now because you don't know why and when and where and how. I'm going to go through the discussion. Then we'll go back and check our beam. So guys, the code, so I kind of snapped this area from the code, and the code is talking about minimum reinforcement, And before I start, why do we need to have a minimum reinforcement? I'll explain for you. Can I ask you a question? Can we have a beam with zero reinforcement?
No.
I know. I need so many guys to say, can I build a beam plain concrete without any reinforcement?
You can, but it won't do you much good.
Yeah, two problems with this one. If I make my beam out of plain concrete, there are two problems. One is the capacity of the beam is so little because concrete cracks at a very early level because it's 1/10 of concrete compression, if you agree. But the other problem which you're not paying attention to, which is it is a brittle failure as well, because concrete is a brittle material. Whether it fails in compression or tension or shear, it fails brittly. It means it doesn't give any warning of failure. And that's why the code has to add some, ensure that there is a minimum reinforcement, okay? That is the reason, to ensure the ductility of your beam. In tension, not in compression, huh? In tension, not in compression. And so where this is mentioned in the code, it's 10.5.1. And again, for the sake of time, there are two ways to check that. You can go to this condition and simply you have to make sure that your beam capacity is larger or equal than M1.2 M sub CR. Does anybody in this class still remember M sub CR? Did you learn anywhere if you study the previous, last week, I'm saying, last week. Did you learn anywhere in some called M sub CR, not MR, M sub CR?
Is that a critical moment, bending moment?
CR is not critical, it's called cracking. Cracking, not critical, cracking. So the cracking moment, that's called cracking moment. And guys, we talked about cracking moment when we have a plain concrete beam, a beam that has no reinforcement. So this cracking moment, as soon as the tensile stress at the bottom fiber arrives at something called F sub R, which is modulus of rupture, then your beam is going to fail. Yes or no? Okay. Okay, fine. Anyway, so let's go right away and make it easy for you. I typically go into the details, but looks like you guys are not in the mode today. Okay, so here is the bottom line. The bottom line is we use this equation here to find what is my area of steel minimum, which is very simple. You have to say 0.2 times the square root of F prime C divided by F field multiplied by B times H. And B sub T is simply the width of your beam at the tension side. Okay? And because our beam is rectangle, it means the B sub T is equal to the B. Same width of our beam. That's the bottom line. Okay? I typically go into more details, but I don't see any response today. So you guys suck my energy. Okay, so let's go to this equation here. As I said before, it's as simple as 0.2 multiplied by F prime C square, like square root, divided by F field B sub TH by numbers. So 0.2 square root of 25, because that's my F prime C. And then the width is 450 divided by F field. But remember, please, I need to change the color for this one, because that's a very common mistake. Because all the way we use D, however, this is the only time I use H, not D. So probably I need to recolor this number, because to bring your attention, please, if you want to find what should be the minimum area of steel, use the H, because that's where the code says, the code is saying H and doesn't say D. And when you do the math, you will see the minimum area of steel is 1012.5. Then are we okay? Are
So
we okay?
Yes.
Yes, because the area of steel that we will actually provide is 3500 here. You provide 530 m, and your area of steel is way 3 times or even more than the minimum area of steel. So we are above the minimum. It means we are okay. There is somebody is about to say something. There is someone is trying to say something.
I got the answer, sir.
Thank you. Okay, guys, here is, I think, what we should break. We will discuss this slide and then we break. So what happens here, guys, this kind of a visual representation of what should be my maximum and my minimum area of steel. So what you see here, there is an arrow, and this arrow simply, it's a line of numbers that we are going to represent our reinforcement ratio. Our reinforcement ratio in my beam. So there are two thresholds. For sure, we don't have a minus. So minus negative doesn't exist. You can see start here from 0. It means if I have 0, it means I have no reinforcement. So this line, it means it's a plain concrete. This line here, it means plain concrete, no reinforcement. Then what happens is early on we keep talking about like failures and beam and compression and tension. Guess what? This line here, it represents the balanced failure. So if your reinforcement ratio is equal to rho balanced, let's say 2.2% for F prime C25 MPa, then what is your failure mode? Balanced failure. How about if I have some extra rebar? So this will turn my beam, will push my rho into this zone. And in this case, what happens? It means this zone is compression failure. So that balanced failure is here at this line. And then beyond the balanced failure, it's a compression failure. Bad. I put here red. So because it's red, it means it's brittle. It means we don't want our beam to behave this way. Okay, now what happened is, how about the code says you have to provide something called the area of steel minimum, which is here. So this box here, it is your area of steel minimum, And so also you cannot add less than area of steel minimum. In between the minimum maximum, I put it here in green and I said okay. So guys, please, I'm gonna label this and probably have to edit my slide. So this is compression failure. This is compression failure. So that's this area is compression failure. And this line here is a balanced failure, because balanced failure is just 1 point. If rho is equal to rho balanced, so that's balanced. And then what happens here? This area here, the green one is tension failure, and we would like our beam to be in between, below the maximum rho balanced, and the area of steel has to be above this point here. Okay. Now there are some marks, guys, coming. There are some incentive coming. So please, if you're sleeping, wake up, and then I'll ask one question. I'll give you some mark, and then we go for a break. Hello, you guys are ready?
Oh yeah.
Yes.
Okay. Now, we know, I think we know, at least I know that if I'm designing my beam and then my area of steel, I'm trying to estimate just like here. Look at this. I estimated the rho balanced 2.2%. I estimated my rho for my beam 0.92. This means, it means I'm somewhere here. Okay. So that means I'm less than rho balanced. And so I know that what we discussed before, what happens if I found myself here, okay? I'm gonna give you the answer because that's easy, because I said it several times in class. If you found that your rho is more than rho balanced, it means you are at the right zone, the red one. This means compression failure, it means bad. What should I do? Should I let it go and continue my design? Obviously, no. What we have to do is, no, we have to stop and do something. What can we do? One of 4 options. This is at the very last slide of my last presentation. You need to change the width of your beam. If it's allowed, you need to change the depth of your beam. It's allowed by the architect. You need to increase the F prime C if you are still within reasonable between 20 and 40 MPa. And then finally adding compression rebar. I guess you guys remember that that was exactly a last class. Now the question for Mark is, what if I'm doing the estimate and I figure out my area of steel is less than area of steel minimum? What should I do? Let's see. Show your hands, please. Is that Domenico? Do you want to answer or you just have a question?
No, I'm going to try to answer.
Okay, go ahead.
Maybe either decrease your beam width and beam depth if you can. Basically everything you said about compression failure, but the opposite.
Okay, thank you, sir. Anybody else has input?
What was the question again, sir?
Okay, can you please, Domenico, put your hands down? So the question was, if my beam, as I'm doing calculation and I found out my beam, the rho is more than rho balanced, then I know it's compression failure. I know what to do, whether increase the beam depth or width or increase F prime C or add compression rebar. And so this is what I do if my failure is here, compression failure. But my question is, which this is for Mark, what if I'm doing during my calculation, I found out my area of steel is less than what's specified by this equation here. For example, by number, let's say I found the area of steel minimum is 1012.5. Look at my screen, if that's my S minimum. However, from my formula here, and after I chose 225M. So if I choose 225M, so this my area of steel is how much? 1000. 2 times 500, 2 times 500. So this equal 1000. What should I do in this case? So my area of steel is 1000 and my minimum area of steel is 1012.5. What should I do? Okay, so we have 1, 2, 3, 4. I haven't heard Brody for some time, so let's get Brody.
You could increase the diameter of the bars or the amount of bars, like just increase the area of steel, if possible.
Okay. Now let's get Mahdi.
I was gonna say same thing as Brody.
Okay, let's get Jelly.
Just add 2 bars on top of the beam so that you will be able to make your beam into a ductile, even though it was in the beginning a compression failure.
Okay, thank you. So Mahdi, you got 2 marks. Mahdi got 2 marks. Also, Brody got 2 marks. Guys, that's correct. Here is the answer, and then we have a break. So if you are into this zone, so the answer is no. You cannot stop, change the depth or F prime C or add compression rebar. How about if you are here? All you have to do is push it to the minimum. So if for example, if I have here a 225M that provides 1000 millimeter square of rebar, and then the area of steel is minimum is 1012.5, looks like there's no choice. I have to add one extra 25M or maybe 20M to bump up my area of steel more than AS minimum. Okay, that's the answer. And thank you for both Mahdi and Brody. And guys, I will take 10 minutes a break. We'll see you back here at 2:10. 2:10, please.